Hey there, class. We're going to look here at example 9 from our Honors Physics 1 notes. So basically what we have here is we have a ball from example 8. So example 8 was an example I did before, and I'll put the link in here so that you can check that out if you haven't already checked that one out. But basically we're dropping it from the same height. This time the ball strikes the ground with a speed of 18.25 meters per second. So if you again go back to example 8, you'll see that this is actually slower than it originally hit the ground with. So that means there must be some kind of energy loss in our system. In that system, the loss of energy comes from the air resistance. The air resistance is a, we're going to call that an external force in our system. Okay, so that external force does work on our system, and as it does work, it actually takes away energy. So once again, taking a look at this, basically, again, some of the very same things that happened before, so I'm not going to spend a lot of time talking about this, but basically it's dropped, so there's no kinetic energy, all potential. So our starting energy is just potential energy, and at the end, it's going to be all kinetic because, again, it's at the ground. This time we are told that it actually has a velocity. At the end, we're told what that velocity was as opposed to asked what that is. Now, the reason I've drawn this dot here in the middle, the center of gravity, is because I want to talk a little bit about what is going on. So basically, we do have a force of gravity. The force of gravity is on this, I guess it was a ball, right? It was on the ball because of the Earth, and that's a downwards force. Now, as this falls, it's going to experience a force of drag, sometimes known as just air resistance, and that's going to oppose the motion. So at this location, again, this is moving downwards, so it has some velocity downwards, and the drag force, which is on the ball by the air, is going to act on this. Now, what you need to know, this air resistance does change throughout the duration of this problem. So that is why in our problem, it actually says find the average force. Okay, to truly find this problem, we would need to know some calculus because the air resistance changes as it falls, and we're just going to assume an average force over the duration of this time. So basically, the work that's done here, this work that's done, you can think of it as the work being done by the air resistance, which is the force of drag, and times the displacement. Now, one of those is going to be a positive, and one of those will be a negative. I don't know if I defined a positive direction in this problem. It doesn't look like I did, but tell you what, for the sake of, actually I must have, because I see over here I have downwards as, you know what, let me get a black pen. That's what I usually use. So I must have called downwards positive because I noticed that my final velocity is positive, and so yeah. Basically, when we look at the work being done, here is going to give us a negative force, okay, because that's up, and a positive displacement, so that will actually be negative work being done. So again, the way I like to think about this is it's removing energy from our system. So in a strategy here, basically what we have is we have an external force acting on it. So mechanical energy is not conserved, okay? So it's not conserved. So what we need to do is we need to account for this lost, and you notice it's in quotation marks here, this lost energy as external work. Now again, I want to emphasize here that energy is really never lost. It's never destroyed. It's never misplaced. It's simply put somewhere else. And in this case, it's being transferred, okay, to outside of our system. Our system being the, I guess, was it a ball? I think it was a ball in the Earth system. So the energy is being transferred out of the system into the air. The air is not part of our system, so therefore it's being transferred there. So as we see, this equation here is familiar to us because this is the conservation of energy equation. And again, this does not apply. Let me be very clear on this. this does not apply in this situation, okay? Because we have energy being transferred out of our system. So that's a red flag as far as that goes. So you might say, well, how do I account for this energy that is transferred out of the system? Well, basically, we just have to put in another term here. And that other term is going to be the work that is done. Okay, and that is the way I'm going to do this here is it's going to be negative work because it's removing energy from that initial amount. The initial amount will be the most. This gets removed from it, and therefore that's going to equal the final. Amount of energy. Okay, so taking a look at this here, our original energy was the potential energy, which is m times g times the original height. Our kinetic energy is 1/2 times mass times the final velocity squared. And the work done is going to be the force. In this case, again, this is the force of drag. Come on, write for me here. Why isn't it writing? Ooh, I had the eraser, that's why. So this is going to be the force of drag times the displacement. Now, while I had the video paused, I realized that if I use the vector nature of these force and displacement, it's going to account for the fact that this is going to be negative work. So I'm going to actually remove that here because it's going to take care of itself when I actually substitute these things in here. All right, so what I'm going to do now is I'm going to pause. I'm going to do the work to basically isolate this drag force, this air resistance, and I'll pick up with you once I've done that. Okay, so I substituted my numbers in, and again, the final velocity was 18.25 meters per second, so I'm going to make sure you square that. The original height was 25, and of course the displacement here was the positive, again, just to indicate here this is positive. That's a positive 25. And now, you might say to yourself, well, wait a second, there's a red flag here, right? What does m equal? And you know what? We don't know. So I'm just going to say we're going to leave our answer in terms of m. In other words, m is going to be in the final answer. So that's what you're going to see here in just a moment. So I do actually end up calculating this out, do the math on the top, and you get this number here times m. Now this is not a unit, this is a variable, and we're going to divide that by 25, which turns out to be a negative 3.14 m. And again, m is not a unit, m is mass. Okay, so a couple little details here. Once again, due to the fact that the drag force is upwards and we call down positive, that means this is going to be a negative direction. One also thing to note here is, again, this m is mass, okay? And so what this means for us, okay, again, the implications here are this answer changes depending on what our mass is. Mass does have a bearing on how much drag force we experience. So wherein before in our previous example, mass just canceled out, that doesn't actually happen here. So mass is an important thing. Of course, we don't know it, so we're going to leave it in terms of m.